Every summer, thousands of wildfires erupt across Europe. Some grow so fast that within hours, entire forests are consumed, wildlife is displaced, and nearby communities are forced to evacuate. For firefighters, every minute can mean the difference between containing a small blaze and battling an unstoppable inferno.
This map shows the distribution of burnt areas across Europe and the Mediterranean throughout 2024. Data from the European Forest Fire Information System indicates dense clusters of fire events, with the most severe scars, highlighted in the darkest red, exceeding 5,000 hectares. To mitigate this destruction, automated early warning systems must identify a thermal anomaly the moment it ignites. However, engineers attempting to build these alerts face a rigid physical bottleneck in satellite sensor design. The challenge is that no single sensor can provide both instantaneous detection and high-resolution confirmation. To see the entire hemisphere at once, a satellite must sit so far away that it loses fine detail. To see that detail, it must orbit so close that it can only view a small sliver of the Earth at a time. Geostationary satellites maintain a fixed position relative to the surface, offering continuous monitoring, but at a very coarse scale. Conversely, polar orbiting satellites perform high-detail, low-altitude sweeps, but they may only pass over a specific coordinate once or twice a day. Relying on one sensor type creates a trade-off. You either accept detection delays that hinder early response, or you accept a high rate of false positives because the sensor cannot clearly distinguish what is burning. Researchers at Fundatio Links proposed a solution that bridges this hardware gap using a multimodal machine learning architecture. They developed a coarse-to-fine pipeline. Instead of a single satellite trying to do everything, independent orbital systems are algorithmically chained together. The first node acts as a first alert, using a high-frequency temporal model to identify emerging anomalies across massive areas. Once flagged, data flows to a disambiguation node, cross-referencing the alert against diverse tabular logs and image tiles to verify the fire. By fusing these disparate data sources, the pipeline translates conflicting orbital constraints into a single operational tracking service. The pipeline begins with the near real-time temporal detection layer. This layer relies on the MSG Severi sensor, which scans the area of interest continuously to identify thermal signatures as they emerge. However, the spatial resolution of Severi is extremely limited. As seen in this thermal map, the data is highly pixelated. A single pixel covers several square kilometers, which often causes different heat sources to blend together. When this coarse data is used in isolation, the resulting F1 score, a measure of a model's accuracy, is only about 64%. The model can detect heat, but it cannot easily distinguish a new wildfire from an industrial furnace or a bright solar reflection off a lake. Severi provides the speed required for an early warning, but it lacks the contextual detail needed to trigger an expensive emergency deployment. To filter these alerts, the pipeline triggers a verification layer. This shifts the focus to medium-resolution polar orbiting sensors like MODIS and VIRS. Teaching a model to separate a fire from industrial noise requires a massive, perfectly labeled historical dataset. This hexagonal map illustrates the scale of that dataset. It contains over 9.5 million thermal detections collected across the Mediterranean between 2012 and 2022. Each of these hotspots was labeled by cross-referencing its coordinates with the verified EFIS database to confirm whether a real fire occurred at that time and place. This chart shows the first disambiguation branch, an XGBoost classifier. Using only raw MODIS or VIRS data, the baseline F1 score is 46.88%. However, by fusing diverse features like time of day and previous hotspots, the model's accuracy jumps to 80.53. By running the XGBoost and ResNet models together, the pipeline ensures a robust disambiguation process, where one model's spatial understanding backs up the other's data analysis. The operational value of this integrated system was demonstrated during the 2023 Greece wildfires. In the region of Alexandroupoli, emergency responders had to manage complex terrain and sensitive parklands while tracking a rapidly moving fire. First, the low-resolution Severi loop flagged a temporal anomaly in the area and immediately passed the coordinates to the verifier. Second, the pipeline waited for the next pass of a polar orbiting satellite to provide more detailed imagery of those coordinates. Third, the XGBoost and ResNet models cross-referenced the new medium-resolution data with local land cover. Finally, the models filtered out the industrial noise and locked on to the verified firefront, providing an automated update of the track over time. This sequence enables responders to trust the alert, knowing the system has already mathematically discarded false positives. The current prototype successfully balances a 64% temporal accuracy for the initial alert with an 80% spatial accuracy for confirmation. Currently, the primary bottleneck is the coarse resolution of the legacy Severi sensor used for the first stage of detection. To enhance this, the next generation of the temporal model will ingest data from Meteosat third generation, or MTG, satellites. MTG satellites provide a significant upgrade to the pipeline's first stage by offering higher spatial resolution and additional spectral channels compared to the legacy MSG sensors. Because the pipeline is modular, as orbital hardware improves, the automated software architecture instantly scales in precision without requiring a full redesign. Early detection provides the data necessary to perform the more complex task of modeling fire behavior. Once a fire is confirmed, the pipeline generates precise coordinates of the firefront and measures fire radiative power. This data is fed into a 3D topographic simulation to predict the fire's path. These verified outputs serve as the clean, noise-free inputs required for advanced models to calculate exactly how a fire will spread through different vegetation. Ensuring this data is accurate is critical. Inaccurate spread models can misdirect resources and lead to failed evacuations, threatening both human safety and biodiversity. By bridging hardware limitations with a multi-sensor software architecture, these models gain the reliable inputs needed to map a fire's path before it arrives.